Hi, everybody. I'm Peter Alvaro. I'm an assistant professor of computer science at UC Santa Cruz. I'm thrilled to be here. Morning keynote slots make a great chunk of time to catch up on sleep, which I confess I've done many times, more times than I would like to admit. So thank you for not doing that. Thank you for being here. This talk is called, I See What You Mean, What a Tiny Language Can Teach Us About Gigantic Systems. And it's really the backstory of a tiny little boutique language called Dedalus that my colleagues at UC Berkeley and I developed during my first couple years at Berkeley, and which sort of formed the rock on which I built all of my thesis work, and hopefully, with any luck, another 10 years of good research. I never got to go back and tell the story of that little language, the context out of which it arose, some of the design decisions we made. So I want to thank you for being my captive audience in this somewhat historical narrative, and expect, like many historical narratives, there's a little bit of meandering in there. So I found it a pretty good template for invited talks of this type to lead in with some really strong statements, statements from my gut that you may not like, something to get your bile up. Statements which, by the way, I have no intention of backing up with evidence, because they just represent my beliefs, But I hope that they'll form sort of a semantic thread, a thematic thread that I can hang some of the technical material that's going to come along the way on. Because, full disclosure, this is a talk that's largely about semantics, and so there will be a little bit of technical material along the way. So, polemic time. Abstraction is sometimes harmful. So abstraction is a thing. It's arguably the best tool that we have in computer science and in cognition generally for managing complexity and for moving beyond it. And at least in computer science, it works like this. We labor at something with computers, and we build an object of significant complexity and perhaps even profound beauty. And then, we finish laboring on it, and it comes time to think about the ways in which it will be used and reused. So we draw a line of demarcation over that object, and we ask ourselves, what are the details that are essential? Well, what does essential mean? Well, essential to some domain that we think the object will be used in. And we obscure the other details of the object, right? We do this anytime we take a bunch of code and put it in a function and make decisions about what parameters to expose, what to return. We do this when we group together a bunch of functions with related functionality into a shared library. We do this when we group together a bunch of functionality behind an API that we expose at our service boundary, but nowhere are these sorts of distinctions so stark as when we design languages. And then, of course, the hope is at that interface boundary, we expose those details that really matter, and then 1,000 flowers will bloom, right? Thousands of applications we could never even have predicted will use our interface and make progress without having to concern themselves with the hardcore details of the implementation, right? And that's a good thing. And sometimes it's even better than that, because sometimes the act of hiding can illuminate surprising things, right? If you blow away a haystack, all of a sudden there's all these shiny needles, right? And so in this talk, for example, I hope to show how by papering over a lot of the distinctions between, different kinds of state representation and different patterns for control flow and synchronization. Oh, that should have gone away too. That's one of the things that was supposed to drop off. We can illuminate the real matter in the domain of distributed systems, data moving and changing through space and time, okay? But it's not all good. When we forget, and we do forget, that abstraction is a universal activity of computer users. It's something that we all do to manage our own complexities. We get lazy and we tend to think of abstractions as these fixed boundaries, these walls. And walls are intended to create borders, to prevent things from flowing across them. Worse still, walls pen people in. And when you think about it, who do we put below the wall on the hard side? Well, we put us, right? We put the geniuses, the infrastructure programmers, the 10x engineers, the library writers, okay? And then who goes above the wall? Well, the despised users. The programmers with neckties, the COBOL people, the SQL people, the analysts. We hate those guys. Read the fucking manual, we say to those guys. And this is something that's always made me really sad, this belief that like library writers and library users are two different classes of people as opposed to two different phases in a programmer's life, or maybe even just the arc of an application's life or something like that. It makes me sad, but it also makes me concerned. Because if we respect those users, by the way, those users are the people who are using computers to like do real shit, get shit done, like do science. They're the reason that we exist, right? If we respect them so little, what are the odds that we're providing the right interfaces for them? One more word about abstraction. There remain certain domains, I'm thinking about one in particular, that remain stubbornly difficult to create the right abstractions for, right? It would be extremely tempting to paper over the complexity of physical distribution. It would simplify the models we use to interact with large-scale systems. But unfortunately, attempts to do so represent some of the worst failures of abstraction in the history of computing. I'm thinking about stuff like RPC, you know? I'm gonna put a function on some other computer and pretend it's on mine. What could go wrong? Or, you know, I'm gonna put a disk on some other computer and pretend it's in my computer. What could go wrong? And the jury isn't out on this one yet, distributed transactions, but it does seem kind of dicey that you could take a database that's literally distributed all around the world and pretend it's on a tower under my desk, and that I can do anything with it I could do with that tower under my desk, okay? I mean, we can paper over these things, and they're gonna do more than leak, right? So, okay, enough about abstraction. Let me talk about me for a minute. I'm not a big fan of about me slides, but I can't really tell the story of Dedalus without telling a little bit about the story of me. And the first thing to get out of the way is that I'm not a lifelong hacker. I'm not one of those people. I screwed around with computers a little bit when I was a lad, but I barely touched them in college apart from word processors. And it wasn't until I moved to the Bay Area around the year 2000 and had to get work that I started writing code for a living. I was working at a company that you may have heard of called Ask Jeeves. It was an early internet company. And my team was called data engineering. We were responsible for the whole life cycle of user-generated data at the site, finding its way through our infrastructure into a SQL server. So I was living in two very different modes at Ask Jeeves. I was writing a lot of infrastructure code, distributed systems code, in a language that you may have heard of called C. And then, I was, moving the data around, replicating it, transforming it, loading it in a database. And then once it got in the databases, I was writing a lot of reports on it in a language that you may have heard of called SQL, business reports and rudimentary predictive analytics stuff. So it really had two hats and switching back and forth between them. And when I used C, I felt like this guy. Because what I was doing was really hard, but the thing was I was good at it. I felt like a superhero. Man, it feels good to write a really big chunk of C code. And if you think it feels good to write it, you would love debugging it. But it made me feel good about myself. That was my comfort zone, And then when it came time to write those reports, write those dashboards for doofuses, I felt like this jerk, Everybody hates SQL, right? But I was living in both worlds, and a couple things started to dawn on me. The first was, if you kind of squint your eyes, the work that I was doing in those two modes, it wasn't really that different. I was data wrangling. I was giving rules about how the data was supposed to move and how it was allowed to change and so on, just in very different ways. And there was something kind of perverse about the infrastructure programming I was doing in C, solving those same problems over and over again, And I began to ask myself, gosh. Oh, the other thing to point out is it felt good to write C, but when I wrote SQL, I wrote good programs. It was easier to get the program right. It was really easy to debug. By the time I checked it in, it was probably right. And so I started to ask myself, gosh, could it be possible to use a language like SQL to write general purpose distributed systems? What would have to change for that to be true? And I can kind of explain these feels, the feeling good thing. When we write programs like C, we're interacting with computers in the way that we were trained to. I learned on a Texas Instruments that a program is a numbered list of instructions that tell the computer, do this, do that, do this, right? So when we think about interaction with computers, it's very natural to think of what a program does is it provides us with a mapping from the program to a set of behaviors that it induces in a system. That's where we like to be. That's where we feel comfortable. A language like SQL, by contrast, gives us a mapping between a program and the outcomes it induces, jumping over the behaviors. It means well, if you will, Because data becomes a common language between the program that the programmer's laboring over and the meaning of the program. The place that the programmer's head has to go as soon as they lift up their hands from the keyboard when they start asking themselves if their program upholds the various correctness properties that they want it to. Okay? I'm arguing semantics, aren't I? I'm talking about semantics, right? So, there's lots of different flavors of semantics, but two that I'll point out right now. Many of you may be familiar with the operational semantics of programming languages, which essentially say a program means what it does to some abstract machine, its behaviors. The model theoretic semantics, by contrast, semantics that are usually associated with formal logic and language theory and to a lesser degree logic programming, say that no, the meaning of a program is precisely the structures that make the statements in the program true. And if our language is a first-order language like SQL, the meaning of a program is the databases that are consistent with it. Meaning is just data, a common language between the program and the semantics. Okay, so here's a boring old query with a kind of somewhat Platonic bent. It says, all humans are mortal, right? In fact, let's just write it down equivalently in first-order logic to make it crystal clear that it says all humans are mortal. For all x, if x is human, then x is mortal. And we ask, well, what does this query mean? We've written it this way. It's easy to see that what it means is it's an implication. It has to be consistent with the rules of implications. If the premises hold, then the conclusions have to hold. So then we say, well, what are some structures that could give it meaning? Well, here's a structure that assigns individuals to a table called humans. And this is not a model of the query, because this is a dangling implication. The premises are true, Socrates is a human, but Socrates isn't immortal. This tells us that if we want to make a structure that contains that is consistent with the query, we have to add at least one more other table, a table called mortal that contains the same rows. So the meaning of the query is what the query does when you run it, but it's also a structure that makes the query true. So, loaded question. Model theory helped us write correct, boring business logic in dusty old databases, but could it help in a really stubbornly difficult domain, like distributed systems? Well, what's so hard? What would we want in a language for programming distributed systems? We would want a language that made it easy to write the good programs despite the bad things that happen. A language that makes it easy to write programs that can tolerate failures, like computers going down, like networks partitioning, and that is tolerant to reordering in the network that happens for a variety of reasons, right? And it's hard to reason about whether my C program does the right thing in all these contingencies simply because there's too many possible behaviors in that space. It's hard to get my head around. Let me give you a little back of the envelope thing. Let's imagine that two endpoints, Alice and Bob, are trying to communicate over an unreliable network. And for those of you who are about to pull TCP out of your ass, just imagine that Alice is partitioned and they're all sending to Bob and Bob is replicated, okay? Where's your precious TCP now? But let's keep the example simple. So Alice wants to send 5 messages to Bob. She does so using a function G. And Bob, when he receives the messages, computes some function F over all of the messages, a function over all the data. I read somewhere that that's called the lambda architecture. Anyway, so in order to decide whether F computes the correct result in all of the executions, we have to consider all of the executions. For example, here's an execution in which messages 2 and 3 are dropped and 4 and 5 are permuted. Does it do the right thing in that one? Well, we could scratch our heads for a bit and say, yeah, F does the right thing in that one. Well, how many times do we need to do this? Well, a quick back of the envelope says, oh man, lots of times, if we just consider loss, we have to consider the set of all subsets of those messages. That's the 2 to the n, 32, that's a big number. Even if we don't consider loss, we have to consider all the permutations. That's 5 factorial, 120. If we consider both, oh man, don't make me do it, but it's for every element of the power set, we have to consider the factorial and take the summation. It's hard math, but it's a very big number. And it's tempting to say, this is garbage. The behaviors don't matter. Many of the behaviors aren't interestingly different. What matters is the outcomes. But if we want to reason about how many outcomes there are, we have to crack into the semantics of these functions f and g. Obviously, if f is commutative, we don't care about that factorial figure anymore. If g retries often enough to overcome failure, We don't care about that power set figure anymore, but we might be concerned about what F does when a message is delivered more than once, which it surely will be if G retries, right? So we have to convince ourselves of another algebraic property of F. Is it idempotent? And if we can convince ourselves of all three of these things, victory, right? Because all of those different behaviors collapse down to one. But how do we convince ourselves that our program has these algebraic properties? Genius, maybe? I don't know. We have few tools to assist us. So queries seem promising, but there would appear to be this expressivity issue, right? Because queries aren't a real programming language, right? I've been seeing a bunch of stuff on Twitter where people think they know what programming languages are, or they think they know what programming languages aren't. Well, there does seem to be an expressivity issue with queries as we understand them, right? Because queries just interact with static data, right? The data in the query model is just sort of there. It's just sitting there, right? And queries walk up to the bar, and they kind of unroll themselves, right, into a tree, a data flow tree of operators, relational operators. And when they reach the leaves, they pull the data, and then data flow goes up the tree. And that's all well and good, but that doesn't seem like programming, right? That's like Q&A. Of course, we have this other model of queries that's been around forever but has become very important recently, the streaming model. The streaming model is interesting because it's very much the dual of the other model, right? In the streaming model, the data isn't just there. What's just there is the queries. They're like instantiated in the network, and the data walks up to the bar, and the data just walks right out the back door. It just flows right through, and data and control go in the same direction. That's pretty interesting. But it gets really interesting when you start imagining hybrids of these approaches. Like, what if I had imagined a stream of requests, like API calls, and then I do some pattern matching, I filter them, I probe some static internal state. If the lookup succeeds, I generate a new event which sends a new message. This is starting to look like a very general model of computation. This is kind of akin to, event loops in an actor-oriented programming language like Erlang. And, while I was still at ask.com, I started to have these thinks. And when you start looking at the world in this way, things start to look different. You start to have these aha moments like, oh my gosh, like a web server is just like a join between a stream of requests and some static content, right? All you have to do is squint a little bit and say, I can see a bunch of calls to an API, a bunch of HTTP calls as records, and I can see a bunch of files on my file system as records, and it's just a matter of joining them up and projecting them. And some of you are probably saying, oh, please, man. This isn't a web server. This is just like a high-level sketch of what a web server does. This is boring. Sure, fine, fair. So Hellerstein's inequality establishes that data independence, the property you get when you separate logical representation from physical implementation, is a huge win whenever it's the case that the rate of change of the environment is much greater than the rate of change of the application. And this was a slam dunk in dusty old databases because your like boring business logic, like how do I know what floor Scott's on and when he's eligible for a promotion, changes like glacially slowly compared to physical changes like you rebuild your indexes, you swap out a disk, you upgrade your hardware. But I would argue that like in the cloud world, the magnitude of this inequality is so much greater, right? Like the right decisions about the hard stuff implementing a web server, like what data structures and algorithms should I use? What caching strategies should I use to make lookups fast? What's a good partitioning that avoids hotspots? The answers to those questions are likely to change all the time, maybe at every request. And it would be a huge mistake to delegate responsibility for fixing those choices to some genius programmer, right? It's the kind of decision that you would want to offload, and I don't mean to trivialize the difficulty of this, but that you want to offload to an optimizer that can make the right decision on a request-by-request basis for how to implement a particular interaction. So, queries seem promising, expressivity is improving, but let's take a step back and take a look at the pieces parts out of which queries are made, the fragments out of which we assemble query languages, and ask what we have, what we need, and what we don't need. So as I already showed you, most query languages like SQL are composed from a small algebra of relational operators, selection or filtering, projection or transformation, and join or composition. And if we take just those three things together, we get the conjunctive queries. We can answer simple questions, implicative questions, like, given what I know, what follows? And SQL actually adds the notion of negation to this algebra so that I can ask questions like, given what I know and what I don't know, what follows? I could add if you like, a blacklist to my web server. Now, unfortunately though, classic SQL doesn't have any way to express recursion, iteration, looping, features that we usually think of as being fundamental to the idea of computation. But there is a language that I encountered when I first joined Berkeley around 2009 that adds to the language of conjunctive queries a least fixed point operator that allows you to define relations recursively. That language is called Dedalus. And it allows us to express transitive closures and things like this. So don't worry about the syntax. I'll talk about the syntax more in a minute. But with the power of Dedalus, I can add a file system to my web server whose directory path structure is recursively defined as a tree, right? I can say the path to some file is / and the file if the file has no parent. And it's the parent's path / the file if the file has a parent. And we might need to go around that loop an arbitrary number of times depending on the depth of the file in the tree. So that's powerful. But there is this question, what happens to that beautiful, data-centric, model-theoretic, implicative semantics when we have looping? Does everything go haywire? Well, luckily, it doesn't. It stays beautiful. The model-theoretic semantics of Dedalus say that the meaning of a program is its minimal model. Model, I've already sort of showed you. There's nothing missing. There's no dangling premises. Minimal means there's no extra crap. There's no unsupported data that isn't that wasn't derived by one of the rules. Let me show you precisely what I mean. So here's a really simple data log program. By the way, data log programs can be viewed very directly as implications with the premise on the right and the conclusion on the left. The way to read it is, if the right-hand side is true with some bindings, the left-hand side must be true with those bindings. So this program says if you're pending something, you should deliver it. Oh, by the way, you're pending something. So when we ask ourselves what this program means, we provide databases to the program and ask if they're minimal models. And so like, we can throw away this one database right away because it's not a minimal model. It makes the premise true, but not the conclusion true. And we can throw away this database too, because although it's a model, it's not minimal. It has extra crap in it. It says we delivered bar when it was never pending. We take that away, and that leaves us with the meaning of the program, exactly this database. So the programmer writes the program, they're imagining that database, and then that database is also the semantics of the program, right? But two interesting things pop out. As one I've already said, data becomes a common language between the programmer laboring over their program and the world of meanings where they go to ask if their program is correct. The other really interesting detail about Dedalus is that those outcomes are completely independent of execution order. As you'll see in a moment, it doesn't matter what order our data appears. It doesn't matter what order we schedule computation. There's one meaning of the program. Here's a very famous Dedalus program that computes the transitive closure of a link graph. It says, you know, if there's a link from 1 to 2 and a link from 2 to 3, then there must be a link from 1 to 3, right? The interesting thing is now this has a bunch of features that we didn't have in the other program. It's got joins, it's got recursion, it's got multiple inputs. But our demonic scheduler and message deliverer can just randomly pick inputs, schedule rules, substitute stuff in, fire them, draw conclusions, jump around, pick some other input, fire a rule, draw a conclusion, jump around. Doesn't matter what order this happens in. We produce one unique answer, the fully connected paths. So many behaviors, one meaning. We've got this mapping that we wanted. Now, when we write programs, a lot of the time we do reason between programs and outcomes, but sometimes we have to reason in the reverse direction. Like when we debug, there's some answer that we got from our program running. We don't understand why. We want to know why it produced that. And that would appear on the surface to require us to peel back that veil and look at the ugly world of behaviors. But luckily, if we use a language like Dedalus, that's not true. So here I have an answer. There's a path from 2 to 4 that I might be curious about why it's in the answer. And if we collected lineage, something that's very straightforward to do in Dedalus, we get a very direct, order-independent, compact answer, which says, well, 2 to 4 is in your answer because you had this data in your model, and it was implied by this rule given that data, and then transitively down the tree, and that data was implied by other data given other rules, and so on and so forth. So this gives us an order-independent explanation of why something was in our output, which is nice. But even more interesting than that it allows us to ask and answer these what-if questions. For example, we could ask, well, what if I deleted some of that base data? Would I have to delete the derived data? And it's easy to see because redundancy of support is manifest in this structure, that if I deleted that data, I would lose one of my proofs, but I would still have another proof. Now, this kind of reasoning has been useful in dusty old databases for stuff like view maintenance. Like, I deleted some base data, do I or do I not need to delete the derived data? In this case, the answer would be no. But it gets really compelling when we think about doing this for a distributed system and representing some of the inputs as facts like, this replica is up, or this network is not partitioned. Because then we can look at the lineage of good outcomes and ask questions like, would the outcome still be good if I lost a replica? Spoiler alert. So Datalog is really cool, right? It gives us a way to write down programs that don't care about the order in which they're executed. A really nice property to have in environments in which we have limited control over the order in which data appears and the order in which computation is scheduled. Environments in which controlling those orders may have prohibitive costs. It's tempting to ask, what happens when we put negation back into Dedalus? What happens to our semantics then? And I'm sorry to say that everything goes to hell then. Okay? So like, here's a program that I don't recommend you write that uses self-reference and negation. It says, you have some input, you have some transaction. It says, if you have a transaction and you haven't aborted, you can commit. And if you have a transaction and you haven't committed, you can abort. Databases actually work this way. But unsurprisingly, this program doesn't have a unique meaning. It has two alternative meanings, okay? We could commit or we could abort. Well, that's not that interesting because that's exactly what the program says to do. But what's interesting is which meaning we end up at is going to depend on the order in which we schedule the arrival of data and the firing of rules, right? So like, for example, if I light up this data and then I light up some rule arbitrarily, say the first one, I substitute it in, and I haven't concluded abort, so I can conclude commit. I put commit in my answer and I say, yes, commit. And then maybe, I don't know, on another replica, seeing the same input, we fire the rules in the opposite order, and the other replica concludes abort, and that would suck. I mean, the intuition here is when a program logically has more than one meaning, its implementations have non-deterministic executions. And that's something that we should watch out for, right? Oh yeah, the point to make is when we go to fire that other rule, we're locked in. That other rule can't conclude abort, but it would if we did it in the other direction. And we shouldn't be that surprised that when we arm ourselves with the power of self-reference and negation, we can get ourselves into trouble, right? We can say crazy shit. Because, with the power of self-reference and negation, we can start to utter paradoxes. We can say, the set of all sets that don't contain themselves. The barber is the man who shaves all the men that don't shave themselves. It's Russell's paradox, right? Or this sentence is false, true or false, Tarski's paradox. In fact, I can't think of any logical paradoxes that don't require self-reference and negation. Exercise for the viewer. So I like query languages because they mean, when you write a query, you mean what you say. Data is a common language between meaning and laboring. And Datalog's interesting because we see that there's this rich, intimate connection between talking about what you don't know and having to commit to particular orders to get deterministic results. Datalog's also interesting because Lineage is cool. Lineage reveals redundancy and independence of support for good outcomes. We can use that to reason about whether those outcomes are robust to bad things that could happen in an execution. But we're still not quite there yet, right? And this kind of is like the work that I started to do once I was at Berkeley and got frustrated with Datalog because it didn't do everything I wanted it to do. So I showed you this gadget, right, that I said was kind of like an Erlang event loop. But this isn't really a protocol, right? We want to start building protocols. They're the building blocks of distributed systems. So to turn this event loop gadget into a protocol, well, at the very least, I would need to instantiate more than one of them, right? And then I would need to arrange them in such a way that the conclusions of one became the premises of another by sending messages, right? And in fact, it might even be cyclical, because I might be implementing like a multi-round protocol like Paxos or two-phase commit, okay? And when I look at my data flow in this way, it looks kind of cool and molecular. But I have to admit that those dotted lines are different from the other lines, right? There's uncertainty in those dotted lines because I'm communicating over an unreliable medium. I don't know when those messages are going to be received. I don't know if they're going to be received. Something unpredictable happens there. And it's worse than I make it sound because in general, protocols don't just have some static state that dictates their behavior based on how they react to messages. They have dynamic state, which changes as a result of the messages they get. Messages change their state, that changes their behavior, and the messages that they send, we have to worry about something unthinkable happening in this loop, right? We have this back loop in which we draw conclusions from non-deterministically ordered events, and that changes our state, right? So if we're going to write a language that really captures everything that happens in distributed systems, we're going to need to capture time-varying state, that horrible thing that we all hate so much, right? Mutable state. And we're also going to need to capture non-determinism in the execution, reordering of messages, loss of nodes, and so forth. And you know, if we could nail these two things in a nice way, we would have really cracked the nut on everything that's so hard about distributed systems, right? Because distributed systems are hard precisely because disorder happens, and then sometimes we witness the disorder and it changes our behavior. Disorderly environments become disorderly behaviors. So how should we even talk about state in a query language? It kind of almost seems, I don't know, like a contradiction in terms, right? Well, we shouldn't talk about it like this, right? Because we're trying to be logically oriented, and this doesn't make any logical sense, right? I can't get my head around this. We're talking about some value at some time and being the same as some other value. The only way I can get my head around an assignment statement really is to say, well, it partitions our program, right, into the past and the future, which means, you know, there's a clock hidden in there. Every time we pass an assignment statement, we move from the past into the future. When there aren't assignment statements, we didn't necessarily have to do that. And similarly, when we communicate over an unreliable network, the send happens at some time, let's just call it the past, and the receive happens, well, actually, I don't think we can really say anything about when the receive happens, right? So the whole idea behind Dedalus was, you guys aren't talking about time. You need to talk about time. If query languages talked about time, we could capture all these patterns, be honest about what we can't control, be powerful about what we can control. So the idea is we want to take that clock and reify it, make the clock a piece of every unit of knowledge that we have. After all, time is just a device that was invented to keep everything from happening at once. So can we talk about time for a second? You guys are all familiar with the conventional model of time in which we live our lives, in which, you know, sort of time marches inexorably forward and discrete events happen on time, and when you want to talk about the history of an event, it's just sort of everything above it. That makes sense. And the database model of time is actually very similar, because in databases, although there's concurrency, we have a concurrency control mechanisms that linearize it, right? So database model of time is like the conventional model of time, except when query languages walk up to the bar, they can't talk about time. They query an eternal present, and all the dots sort of converge to one. You're probably also familiar with the distributed systems model of time due to Lamport, in which processes have single timelines that make sense, and they march forward in time, but when time comes to send a message, that message moves forward through space and time. And we can say forward in a well-defined way, because we can posit the existence of a sort of idealized timeline that none of the processes can view that moves forward, and that's what keeps those lines going forward. But if we want to write a language in which time is explicit, a language that dictates the behavior of processes, we certainly can't allow that language to talk about the God line. I mean, if we could, distributed systems would be easy to program, but I'm not sure how we would, you know, implement that language. So forget about the God line. And when you forget about the God line, you have to admit the possibility that, that messages can go backwards in time, at least in the shallow sense that, like, the timestamp on the receiver when he gets the message is lower than the timestamp on the sender when he sent it. And if you wanted to rule out those behaviors, you could. You'd have to rub some Lamport clocks on it. You have to write protocol in Dedalus. Now, it might be tempting to rule out causally impossible executions, like this one. I send a message to some other person, and she replies, and I get the reply before I sent the message, because that just can't happen, right? That's crazy. Well, I don't know. Like, what if we did that execution and we sent the message and then she went into like a long GC pause and then I crashed and I started to replay from log. Okay, so like it's not clear to me that can't happen. So I think we can't constrain receipt time whenever we communicate over an unreliable network at all. Not in our model, not if we want to be honest about everything that can go wrong. So that's the whole, you take all of that and you come to like the Dedalus philosophy. So the first big shift is knowledge is not a persistent thing. Knowledge is just ephemeral. Here's some knowledge, a string called data, in a table called data, but it only has meaning at some discrete time, 5, on node 1's clock. Knowledge is ephemeral, knowledge is local. Knowledge is a flash in the pan, okay? And viewed in that way, computation itself, the better part of computation, is just setting up the rendezvous of ephemera, right? I can only take some data and some event and combine them to have some new knowledge if I can somehow make it the case that data and the event are in the same place, right? Like, I can't conclude something from something that I know and something that you know. We have to like talk, right? And moreover, they have to be true at the same time at the same place. I can't draw a conclusion from something I know and something that I don't know yet, any more than I can draw a conclusion from something that I know and something that I've forgotten. So computation is rendezvous, okay? When you look at how rules work in Dedalus, they extend data log with 3 types of temporal rules. The first one, the so-called deductive rule, is just like data log. Given what I know, what else do I know? Now. The second type of rule is an inductive rule. Given what I know now, what is true at the immediate next time? I couldn't make the clock go by 1, so I just, but the clock moves is the point. We move the clock when we do an inductive rule. And this allows us to talk about relations between successive states in time. And the last type of rule are asynchronous rules. They allow us to be honest about the control that we don't have on the clock when we communicate over an unreliable medium. The premises of an async rule are true at some time. Its conclusions are true God knows when. Okay? And when we want to implement this in a data log-like language, it's actually very straightforward. We say, every record has a timestamp. Deductive rules say the conclusion has the same timestamp as the premise. Inductive rules say the conclusion has one higher timestamp than the premise. And asynchronous rules say, hey, look, there's this infinite domain of time. We randomly picked from it, okay? Sorry. And this leads to a very straightforward sugar for the programmers. We don't have to talk about the timestamp. We don't have to talk about the constraints. We can just put modifiers on our rules, same meaning, okay? Now, next is a very powerful construct in Dedalus. It allows us to say all sorts of things that we couldn't say in a query language. Because in addition to expressing relationships among facts, it allows us to characterize relationships between states and time. So I can say, these 2 facts have to occur together or not at all. That's atomicity. Or these 2 facts have to occur one or the other, but not both. Mutual exclusion. Or this thing happens and then this thing happens. Sequencing. 3 features that we couldn't express in a query language that now allow us to do things like implement concurrency control protocols. Okay? Another mind bender is that unlike in databases, which with having no time had only state, in Dedalus, there is no state. State is really just a programmatic construct. State is what you get when you say, when you know something, then you know it at the next time. And by induction, you keep knowing it, right? So this set is immutable because if I put something in it, it'll be true at the next time, and then it'll be immutable and be true at the next time. State is induction in time, okay? Like the way that frame rules work in logic, or the way that DRAM works in your computer. Viewed this way, state is not our enemy. State's our dear friend. State is what makes the otherwise unlikely rendezvous of ephemera possible. Like if I say, if I know about 2 events, I should dispatch some new event, what is the likelihood in an asynchronous environment that the 2 events will co-occur? Well, state is what allows us to make them co-occur. Okay? State is our friend, but it's our friend who's sort of a loose cannon, right? Who we need to keep on a close leash because state can record elements of the disorder in the environment. Here's a register, a fundamentally order-sensitive, imperative pattern written in a query language. We say, if you get an update, you put it in your register. Oh, and if you don't have an update, you persist the current value of the register. So obviously, this is a gizmo that's going to be sensitive to the order in which its updates occur, and for which the last writer wins. And here's its brother, first writer wins, which persists whatever it has and updates whatever it has only if it doesn't have something. This is actually an interesting little gizmo because you can use this to convert like at least once into at most once at the cost of spending some state, spending some time. And we can generalize a register to a table where we have to explicitly delete and we can accumulate data, and it all makes sense. It all makes sense as we go through time. Mutable state in a query language. Or the ubiquitous fragment of the ubiquitous distributed counter problem, right? If I have an event, I should bump my counter. And if I don't have an event, I should preserve my counter, right? So next was powerful. It allowed us to control the hand of the clock. We can do all sorts of things with a query language when we can control the hand of the clock. But we need to come clean about when we can't control the hand of the clock. So the async operator lets us be honest about the orders we can't control. Like here's the counter program augmented with some agents who request values of the counter. They wake up, their messages race to the node holding the counter increments and sends messages as side effects of receiving those messages. And there's quite a big deal of uncertainty about which agent reads which value. This is a non-deterministic program. We'd want to be able to know that. So what did time do? Well, space, this was interesting for me. Space would appear to be the thing in distributed systems, but space is irrelevant. It's just data and names, right? I can join on it, I can select it, but there's no semantics. All of the semantic consequences of non-determinism, of distribution, are made manifest in the dimension of time. Distribution can make time unpredictable, and that unpredictability is sometimes bad. But exactly when? Well, to answer when, we need to devise a model theoretic semantics for this crazy new language that has time, change, and non-determinism, and hope that we can keep it simple. Now, there is, from the pages of logic programming, a model theoretic semantics that exactly captures the meaning of these programs. It's called the so-called stable model semantics. And the intuition is, every time we have an async rule, we roll some dice. And the roll of those dice determines a unique model for our program. Problem is, it's an infinite-sided die. So we have an infinite number of models of this program, each of which, incidentally, is infinitely large because of these next rules, because these programs just run forever. They keep ticking forward what they know into time. So infinite number of models, infinitely large, like that's not going to help us to reason about whether our program is correct. Like for example, I provide this program with some input, I flip a coin, and here is one of its stable models. It's infinitely large because everything ticks, and I happen to have picked time 100 for the message to be delivered. Fuck, okay. What can we, so now we're back where we started from, right? We have a mapping that makes sense, model theoretically, from programs to behaviors. But what about those outcomes? Well, what we really want is to apply that same intuition we did in the beginning of the talk, right? Most of these behaviors aren't interestingly different. They create data that is maybe different only in its timestamp. And we want to be able to group those together into an equivalence class. What we want is to sort of take a magnet and extract from that haystack the facts that at quiescence time have become permanently true and are changing only in their timestamp. The facts that are eventually always true. And that looks something like this. Magnet, eventually always true, drop the timestamps. Now we have something that looks like a real meaning of our program. Because what happened in this program? We had a counter initialize as 0, and we requested it. So the counter got bumped to 1, and the request contained the previous value of the counter. It's a unique model despite an infinite space of executions. That's where we want to be. Now, some programs, not this one, have a unique ultimate model. They're confluent. No matter what data you give them, for that data, there's only one answer. And this would be huge, right? Like, if we could show that a program had only one unique meaning, that would mean that its executions were deterministic. That would mean that distributed systems weren't so hard anymore, right? It would mean that we could replicate our computation without coordination, without having to worry about those replicas getting out of sync. It would mean that we could do replay-based debugging, because if something bad happens, it's guaranteed to always happen. This is sort of the holy grail, right? So, talk's over, we win. No, actually. So like many desirable properties in systems, confluence is undecidable. And if I had time, which I don't, I would go through Bill Marzak's brilliant proof of confluence being undecidable. But sort of TLDR, if you could write a confluence checker, you could use it to check if an arbitrary Turing machine halted. And we suspect we haven't solved that problem, which means, that confluence is not decidable. Okay, so Dedalus added to Datalog the ability to talk about what changes and what changes are out of our control. And it left us with a really big language, a powerful language that could implement any system, a Turing-complete language, actually. Too big, right? It didn't help, right? We're back where we started from. So, but it's interesting to consider fragments of this language. Like, what happens if we take away that pesky negation? Well, actually, that's the sweet spot. That's the Goldilocks language, is Dedalus with no or with very carefully controlled negation. Because due to the COM theorem, we know that negation-free or monotonic more broadly, Dedalus programs are confluent. They're deterministic without coordination. We might be concerned about expressivity, but a famous result due to Vardy and later Immerman establishes that this class of programs is at least as big as the polynomial time programs, which seems like a good place to be for distributed programming. We don't really want to exponentiate over the network, right? So the COM theorem essentially says, you can have your state and your asynchrony and your, non-determinism, and you can distribute it too, as long as you're careful about how you combine these paradoxical things, self-reference and negation. And it leads to a really cool pun, really cool for me, maybe not for everybody else, on the word consistent. When a logician talks about consistent, they mean free from absurdity, okay? When a programmer talks about consistent, they mean my replicas don't get split brain. And if you view through the Dedalus lens, it's actually the same idea. So when we commit acts of abstraction, we need to make hard decisions about what to hide. And the hope is that interesting and surprising things will be exposed. With Dedalus, we were very careful to hide a variety of different representations of state, right? Like the difference between events, internal events, messages, rows and tables, cache contents, files on file systems, et cetera. We made them all look like rows. We also hid control flow. Because in Dedalus, there is no control flow except the implicit control flow implied by data flow. And that simplified a lot of programming. In return for those sacrifices, we got a language that makes three things shine out and be obvious. Data is the fundamental unit of computation. Sometimes we can control how data changes, and sometimes we can't, and we need to know when. And one neat little trick that fell out of all this, a sort of side benefit that you get from using a dusty old language and evolving it rather than starting from scratch, is that you can apply old techniques that were never even thought of to have been applied in a new domain. In particular, turning the lens of logic programming on distributed systems, some really neat stuff fell out, right? Like taking a page from model theory, we can look at the meaning, the semantics of the program as just databases, and make databases this common language between the programmer laboring over his program and the world of meanings where they go when they ask if their program is correct. And model theory also establishes this amazing connection between the meaning of programs, the uniqueness of a model of your logical statements, and this really valuable systems property of deterministic outcomes despite pervasive non-determinism in execution. What grows on that? Well, we developed a language called Bloom, which threw away that horrible Dedalus syntax, but saved its semantics, and which ships with tools that allow programmers, that tell programmers whether their programs are deterministic and exactly why they aren't if they aren't. On top of Bloom, we built Blazes, which takes that insight a step further. It says, well, if I can tell you exactly why a program is non-deterministic, then I can probably fix it by adding protocol. What kind of protocol? Well, a protocol that controls ordering when the ordering matters with respect to the result. Now, from proof theory, we got another bag of tricks, right? We got this idea that data lineage, something that's easy to collect in a system like this, provides redundant proofs of outcomes. And when we can show that an outcome has multiple independent, redundant proofs, independent with respect to failure domains, we can prove that our programs are fault tolerant. The fruit of that work is a system called lineage-driven fault injection, which began as an academic prototype, but which I've spent my summer at Netflix building into a production system using their chaos animals. And we hope to take the veil off those results soon. What else grows there? Oh, well, the sky's the limit, but one thing I'm particularly interested in is Eve, a programming environment for non-programmers that legitimately threatens to change the way we think about computers and people and their interaction. Watch this thing closely. So recall, we wanted a language that makes it easy to write the good programs and easy to know if we succeeded despite the bad things. Dedalus's answer to this is, well, abstract away the bad things, but don't hide the complexity. Use model theory to reason about whether our programs are tolerant of loose orderings. Do they have a unique ultimate model? Can we syntactically prove that they do? Use proof theory to reason about whether our programs are robust to failure. Can I show, after running a program, that its outcome has multiple independent supports? What do we want? Dedalus. When do we want it? Eventually. So in closing, some of you might be saying, I don't invent languages. Why do I care about any of this? And I guess what I would say back is, this isn't about inventing languages. This is about committing acts of abstraction, something that we do all the time, right? And so my advice about abstraction, flaky as it might be, is first of all, we don't do a good enough job respecting our users. But a great first step towards respecting our users is admitting that we are them. We write these libraries so that we can use them. Let's respect ourselves. Let's respect ourselves and our users enough to not make concrete, static abstractions, right? Trust ourselves to let ourselves peer below the facade. There's a lot of complexity down there, but we need to engage with that complexity. We need tools that help us engage with the complexity, not a fire blanket, right? Abstraction's gonna leak, right? So make these abstractions fluid. And then finally, and obviously I'm a database guy, so I'm kind of guarantee-centric, but give me the choice between a nice syntax and a nice semantics, something that feels good and means well, I'm gonna choose means well every time. Because the reason we write programs isn't to give ourselves warm, fuzzy feelings. It's to get shit done. And then, in the interest of coming clean, it is about inventing languages. Inventing languages is really fun. And so I know a great place. So if any of you are interested in spending the next 5 or 6 years screwing around, inventing languages, building systems with them, studying the systems with the languages, studying the languages with the systems, I'm looking for PhD students. Come join me. Thanks.